Welcome back to Machine Design course. We'll continue with our topic fatigue failure theory. This is part B, and we will continue to see how we could develop SN diagram in this video. The stress life approach SN. It is a stress-based model which seeks to determine a fatigue strength and or endurance limit for the material so that the cyclic stress can be kept below the level and the failure avoided for the required number of cycles. So the SN diagram could have low cycle fatigue and high cycle fatigue regions. The low cycle fatigue region is that the region when we have less than 1000 number of cycles, and the high cycle fatigue or HCF is the region when we have more than 1000 number of cycles. Okay, so here we have a SN diagram again. We have HCF SN diagram or high cycle fatigue diagram. Why? Because it starts at 1000 number of cycles. So number of cycles are more than 1000. And you see that these are experimental data and is scattered between the lower and the higher band. This specific one is for the route steel. Okay, so it's steel with the ultimate tensile strength of less than 200 KSI. And here we have SF or fatigue strength divided by ultimate tensile strength. So you see that on lowest number of cycles, when we are below 1000, the fatigue strength is almost equal to SUT, yeah, but not exactly, but almost, yes. Or we could say that at 1000 is SF or fatigue strength is 90% of ultimate tensile strength, just to get the safe side, yes. So we want to go with the lower band because it is the safer region. And then we see that by increasing number of cycle linearly in semi-logarithmic plot, okay, so this is a semi-logarithmic plot. You see the x-axis is a logarithmic. So we have 1000 and then we have 10,000 and they are equally distanced, yes. This is 10 times bigger than this one, yes, at the previous point, but has equal distance. But the y-axis is just a linearly space and is a normal axis. So that's why I call it semi-logarithmic plot or diagram. So on this type of diagram, you see that we have a linear reduction in the fatigue strength. So by increasing the number of cycles, the fatigue strength decrease linearly. Okay. But then for the steel case, it doesn't go below a specific limit. So we call it endurance limit or endurance strength or SE. And we see by increasing the number of cycle, material could keep its strength. And we have a fixed fatigue strength which is equal to the endurance strength. Okay. This is basically based on the empirical data. This is what you have watched in the previous video, and these points and dots, these dots are coming from those specimens that we put in the machine. So each of these dots are coming from one specimen that goes under a specific number of loads at at the specific alternating strengths. Also, or we could say that we are putting that specimen under specific alternating strengths, and we are looking to see at what number of cycle it breaks. So we need to put lots of those specimens in the machine and repeat the test to develop this SN diagram. These empirical data for different type of materials exist in books, or there are some ways to develop these SN diagrams theoretically, and also those methods coming from imperial data. We will discuss these methods in coming slides. Note that the fatigue strength, or SF, falls steadily and linearly as a function of n until reaching a knee at 1 million to 10 million cycle. This knee defines an endurance limit for the material, which is a stress level below which it can be cycled infinitely without failure. Okay, so not all materials show the knee or endurance limit. We have it for steel, but for example, we don't have it for the aluminum. But when it happens, it usually happens or around this number of cycles, 1 million to 10 million cycles. At the lower bound of the scatter band beyond the knee, an approximate endurance limit can be defined. Okay, so I show that in the SN diagram. I will show it again in coming slide. Okay, so testing actual assemblies, as also discussed in the video, not all the parts and machines go under sinusoidal load, either reverse or repeated or fluctuating loads. So we need to put that part under a specific test. And this is an expensive proposition and is usually done only when the design's costs, quantity, or threat to human safety demand it. So mostly for expensive transportation aircrafts and for trains, they will do these tests. For bicycles, for example, when there is a threat to the human safety, because developing these type of test machines are expensive, very expensive, and we need to break parts. See, like a specimen that we broke, we need to break many parts to see the real fatigue strength of the material. Of course, we could always use a factor of safety or safety factor, and this is what we do for most of the machines, but still for aircraft we want to be 100% sure that aircraft doesn't crash. Okay, so now you know how we could develop the SN diagram based on experimental data. Now we want to see how we could estimate the fatigue strengths, or how we could estimate the SN diagram. Estimating the theoretical fatigue strength SF or endurance limit SE. If published data are available for the fatigue strength or endurance limit of the material, they should be used and the correction factors then applied to them. So if we have access to the experimental data, we will use those experimental data. We don't use the estimation or the theoretical fatigue strengths. No, we'll go with the experimental because it has a better accuracy. And then we need to apply some correction factors for basically to take into account different environment and loads and size, because anyway those experimental data are based on laboratory environment, for example specific temperature in the laboratory. But for machine may operate in a different temperature or a different environment, and we need to use some correction factors. We will discuss what are these correction factors in coming slides. Published fatigue strength data are typically from fully reverse bending or axial loading tests on a small polished specimen. If no fatigue strength data are available, an approximate SF or SE can be crudely estimated from the published ultimate tensile strength of the material. So when we don't have access again to the experimental data or SN diagram, we'll go with the approximation of SF or SE based on the ultimate tensile strengths, and we will apply correction factors. Okay, so what are these estimations? These estimations coming from, again, experimental data, okay? For the steel, say that uncorrected, this is when we say SE prime or SF prime, it means that uncorrected estimated fatigue strengths. Okay, then we need to apply correction factors to take into account the environment of the machine, different load, different size, different geometry, different temperature, and etc. We'll discuss correction factors. But now at this slide, let's see how we could approximate fatigue strengths. So for the steel, in most cases, we are interested in endurance limit, and we could say that the uncorrected estimated endurance limit is equal to half of ultimate tensile strength. And this is when the ultimate tensile strength is less than 200 kilo psi or pound per square inch, or 1400 megapascal. When the ultimate tensile strength is more than that, we could say that the uncorrected estimated endurance fatigue strength is equal to 100 kilo psi. For the iron, we also have very similar equations. We have endurance limit, or we could observe the knee in the SN diagram at about 1 billion cycle. For aluminium, we don't have that knee or endurance limit. So for the sake of estimation or finding the SN diagram, theoretically, we could find uncorrected fatigue strengths at 500 million cycle, or 5 multiplied by 10 to the power of 8, which is 500 million cycle. And when the ultimate tensile strength is less than 48 kilo psi or 330 megapascal, then is equal to 0.4 SUT, or 40% of SUT. So you see that anyway, fatigue strength is less than SUT. You must be less than SUT. And when the SUT is more than 330 megapascal, then is equal to 90 kilopascal or 130 megapascal. For copper alloys, also the same story. We don't have endurance limit, and we could estimate the uncorrected fatigue strength at the 500 million cycle by these equations. Okay, so later we will use these equations to develop a theoretical SN diagram and find fatigue strengths at any other cycles, not only these cycles, not only at 1 million cycle for steel and iron, and not only for not only at 500 million cycle for aluminum and copper alloys. We could use, or we could find fatigue strengths at any other cycle, and we will see how we could find SN diagram or develop SN diagram theoretically for these type of materials. Now we should see how we could apply correction factors and what are correction factors to the theoretical fatigue strengths or endurance limit. The fatigue strengths or endurance limits obtained from standard fatigue test specimens or experimental data, or from estimates based on static tests, must be modified to account for physical differences between the test specimen and the actual part being designed. Environmental and temperature differences between the test conditions and the actual conditions must be taken into account. Differences in the manner of loading need to be accounted for. These and other factors are incorporated into a set of strength reduction factors that are then multiplied by the theoretical estimates to obtain a corrected fatigue strength or endurance limit for the particular application. So you see that they also call it the strength reduction factor because these factors are less than 1, and what we could find from the experimental data or the estimates or theoretical data that the strength is higher than the real strength of the material. We need to reduce it by taking into account different environmental and temperature differences. So where SE presents a corrected endurance limit for a material that exhibits a mean its SN curve, and SF represent a corrected fatigue strength at a particular number of cycles for a material that does not exhibit knee. The strength reduction factors in the above equations are defined below. Okay, so you see that we have SE and SF here. These are corrected one. We have SE prime and SF prime. These are not corrected one. Okay, so this SE prime and SF prime could come either from experimental data or from the estimates. And we had estimate for steel, iron, aluminum, and the copper alloys in previous slides. Please discuss those slides to remember exactly what are those formulas. Now we need to apply these correction factors, and all of these correction factors are either equal to 1 or less. See, we have correction factor for load that will take into account differences of load conditions, size, surface, temperature, and reliability. And in coming slides, we will discuss each of these correction factors. Loading effect. For bending, C load is 1. So because the experimental data and estimates are coming from bending condition, not the axial loading, so C load is equal to 1 when the part goes under bending stresses. But if the part goes under axial loading, then the C load is 0.7. Okay, so it means that the real strength of the material is 70% less than the one we found from experimental or theoretical estimation. Size effect. When the diameter of the part is less or equal than 0.3 inch or 8 millimeter, then the C size is equal to 1. Okay, so you remember that those specimens, they have specific standard. Okay, and when the diameter of the part is comparable to the standard specimen, then we could say that the C size is 1, or we don't need to correct the strengths or reduce the strengths. When the diameter is between 0.3 inch to 10 inch, then the C size could be found by this formula. And D here is in inch, or in metric unit when the D is between 8 to 2500 millimeter, then we could find C size by this formula. For larger sizes, we could use this formula. C size is equal to 0.6. Okay, so for non-cylindrical part, this is all for cylindrical part because the specimen is cylindrical. Okay, but what about for non-cylindrical part? We need to calculate the A95 and D equivalent. So this D equivalent is the diameter that we could use in these formulas. So we need to find the D equivalent first and put it in these conditionals and see, for example, if D equivalent is less than 0.3 inch or it falls between, let's say, 8 to 2500 millimeter, or is more than 2500 millimeter. Okay. So what is A95? An A95 is a portion of the cross-sectional area of a non-round part that is stressed between 95% to 100% of its maximum stress. So here you see that for different cross-sectional areas, we have different A95. For solid or solid round shape, for rotating or non-rotating part, we have different A95. Okay, but for rotating, you don't need to calculate A95. You could simply use D in those conditions or equations in the previous slide. But let's say for solid rectangular, then A95 should be calculated for non-rotating part when the load is cyclic and goes from minimum to maximum. Then A95 should be calculated. Then you should use this A95 in equations of previous slide to find D equivalent, and then use that D equivalent to find correction factor for size. Surface effect. So surface finish could be either ground or machined or cold rolled or hot rolled or forged. The reason is the reason the surface have an effect on fatigue strengths is that different surface finishing could have different effect on initiation of crack and propagation of crack. So we have this formula for a C surface is A multiplied by SUT is ultimate tensile strength to the power of B. And if C surface from this formula becomes larger than 1, then you should apply C surface equal to 1 because correction factors cannot be more than 1. Okay, so let's say for metric units, when we have SUT in megapascal, then we have A and B constant here in this formula. So when the surface finish is ground, then A is a constant equal to 1.58 and B is equal to minus 0.085. Where are these numbers coming from? From experimental data. Okay, so A and B are constant and you could find them from this table. Temperature effect. for temperature less than 450 degrees of Celsius, C temperature is equal to 1. When temperature is between 450 and 550, then C temperature could be found by this formula. Or if the temperature is in Fahrenheit, then you could find C temperature by this formula. Based on data for steels, and should not be used for other metals such as aluminum, magnesium, or copper alloys. So these are only for steels. So if you want to find a correction factor for temperature of other materials, then you should refer to tables of the book to find relevant formula. And finally, reliability. Experimental data are based on 50% reliability. But when we want to take into account the effect of a standard deviation and going for higher reliability, then we should seek for lower reliability correction factor. For 99.9% reliability, then correction factor is 0.753, or I could say fatigue strength is lower. Now we calculated all these correction factors. Okay, so we had this formula in the previous slides. I put it or repeat it again here, just remind you what we are doing. We don't want you to get lost between the slides. So far we calculated C load, C size, C surface, C temperature, and C reliability. Also, we had uncorrected endurance or fatigue strengths either based on experimental data or from theoretical formulas. And now you could just plug all of these numbers into this equation and find corrected or actual fatigue strengths or endurance limit of materials. Okay, now let's see how we could create estimated SN diagram. We said that we could estimate endurance limit or fatigue strengths for one particular number of cycles. But what about other cycles? What about fatigue strengths at other cycles? The bandwidth of interest is high cycle fatigue regime from 1,000 to 1 million cycle and beyond. So we are looking to find SN diagram which starts from 1,000 and beyond. Let the material strength at 1,000 cycles be called SM. So we have strengths here at 1,000 cycle, which is equal to SM. The data indicate the following estimates of SM are reasonable. When we have a bending loading, SM is almost equal to 90% of ultimate tensile strength. And when we have an axial loading, SM is equal to 75% of ultimate tensile strength. So look, we are trying to plot this SN diagram. What the first point is SM. And SM could be calculated by these approximations. SM is the strength of the material as at 1,000 number of cycles. Then we need to find SE for those materials that show knee or like a steel or endurance limit. And for example, for steel and iron, we had already approximation. For steel, we had this approximation that when the ultimate tensile strength is less than 200 kpsi, then SE is equal to 50% of ultimate tensile strength. And that one was uncorrected. Okay, so we need to find first SE prime, which is uncorrected one based on the formula. Then we should apply correction factors to find the real SE at 1 million cycle. At 1 million cycle. This is for those materials with Ni, those without Ni, like aluminium. Also, we had estimation at the, for example, for aluminium, we had estimation for 500 million cycle, okay, and we could find that point at 500 million cycle, okay, 500 million cycle almost here, yes, for aluminium. Sorry, 500 million cycles is here exactly as it's shown, represented in this graph, okay, so 500 million cycles, so now we have this second point, okay, and then when we have these 2 points, the next step is easy. Just we need to connect SM to SE, and since we have a Ni, then here the next will be just one horizontal line. For those without Ni, we need to connect SM to SF and extend it to higher cycles. And now we could graphically find strengths of the material at any other cycles. Is there any way to find mathematical formula also for this line? Yes, the answer is yes, and we see in coming slide how we could develop mathematical formula for this line. Okay, now we want to see how we could find equation of the line. The equation of the line is Sn is A multiplied by n to the power of b, because this is a logarithmic a line, or in a semi-logarithmic, we could say that logarithm of S or fatigue strength is equal to logarithm of A plus B multiplied by logarithm of N. Okay, so we just got the logarithm from both sides, left and right side of this equation. Okay, nothing magical to this point. Where Sn fatigue at any n, A and B constants defined by boundary conditions. So we need to find only A and B constants. If we could find these two, then we could plug in any number of cycle and find the fatigue strengths. Okay. Of course, we could find also fatigue strength graphically, but also it is more accurate to find the formula of the line. So one point is N1 here when the number of cycle is 1000 and we have fatigue strength of Sm, we have this point, and the second point is N2 is either 1 million cycle for those which has Ni, or 500 million cycle for let's say aluminium, and at that point we have Se or Sf. So we have 2 points. We could plug it into this equation, 2 unknowns, 2 equations, and we could find A and B. So the first constant B could be then calculated by this formula, logarithm of Sm divided by Se divided by Z, where Z is the logarithm of N1 minus logarithm of N2. For example, when N1 is 1000 and N2 is 1 million, then Z is minus 3. Okay, so logarithm of 1000 is 3 and logarithm of 1 million is 6. So 3 minus 6 is minus 3. So you could also use this table, but I'm more comfortable of using the formula instead of this table. Okay, but it's up to you. So these logarithms has a base of 10. They are not let's say, natural logarithm. After you found B by having N1 and N2 and SM and SE, then you could find logarithm of A. So it's just here, find the logarithm of A from this formula, which is equal to the logarithm of Sm minus B logarithm of N1. And since N1 is 1000, so logarithm of N1 is 3. So it's equal to logarithm of Sm minus 3B. So now you see that you managed to find B and A, and then having this formula, complete formula, and find the fatigue strengths from any number of cycles.